Hello children, in this video session of today I am going to discuss dimensional analysis. Yes, this is quite an important topic which comes in the very first chapter of class 11 of ISC and CBC. Alright, so this topic is important keeping in mind the board examination as well as the other competitive examinations like NEET joint entrance examination. Alright, so and I guarantee you in this regard that after this session is completed by you, this topic will just be very easy and very simple to you, as simple as water. Alright, so without wasting much time, let us give it a very good start. Yes, my name is Bapender and you're watching eTuition. So the topic on which we're going to talk today is dimensional analysis. Alright, first of all, I tell you that there are some fundamental physical quantities you might have known already, like the mass, which is denoted by capital M. Next one is length, which is denoted by capital L. Next one is time, which is denoted by capital T. Other one is electric current, so which is denoted by capital A. Alright, or in some places it is also denoted with I, but here we shall express it with capital A, right? That's why I'm erasing this capital I for the time being. In some other books you may also find that this has been symbolized with I. That's not absolutely a big deal. Alright, it's only the symbol that matters. And other one is temperature. Other one is temperature, that is denoted with theta, right? This is theta, a Greek letter. Now I tell you what dimensions are actually. Dimensions are the powers. Dimensions are the powers have a look at the definition of dimensions. Dimensions are the powers to which the fundamental or base quantities are raised in order to get the formula of a required quantity. Have you understood? Dimensions are the powers to which the fundamental or the base quantities are raised to get the formula of a required quantity, right? So now let me tell you with the help of an example. For example, you have heard about velocity, right? What is velocity? Velocity V is actually the displacement per unit time. Am I right? Displacement per unit time. Displacement divided by time. As you all know, what is displacement? What is displacement? It is nothing but a length along a straight line path, isn't it? Displacement is a length along a straight line path. It is actually the linear distance between the initial and the final point in a specified direction. It has to be, that is why it is along a straight line path, right? So what is displacement? It is nothing but a length. So let us write capital L over here, and in denominator is time, L by T. So we write it L T to the power minus 1. You all can understand that 1 by T can be written as T to the power minus 1, right? And we denote it within the box bracket or third bracket, right? The basic three fundamental quantities, you know, mass, length and time, right? M, L and T. So we need to write all the three. Since M is not here, we shall write M to the power 0, because M to the power 0 is nothing but 1, right? M to the power 0, L to the power 1 and T to the power minus 1. Is it clear? That is how we denote the dimensions. The basic three quantities M, L and T has to be written everywhere. okay, in the dimensions of each physical quantity. Keep it in mind. After that, let me tell you one more, that is momentum. So let me tell you one more, that is momentum. So what is momentum, which is denoted by P, is equal to mass into velocity, right? Mass into velocity. Mass multiplied by velocity. Mass multiplied by velocity. So mass is something which we denote with capital M. I told you before already. Mass M multiplied by velocity. The dimension of velocity we got already, Lt to the power minus 1, right? So let me write Lt to the power minus 1 here. So all we are getting at the end is m to the power 1, L to the power 1 and T to the power minus 1, isn't it? So here in these two dimensional formulas, actually all we can write is the dimensions of velocity are 0, 1 and minus 1 on m, L and T to the power. Yes, that's the way we write. That's the way we write the answer. Okay, I'm writing C. Dimensions of velocity are 0, 1 and minus 1 on M, L and T. That is how we write the dimensions. Dimensions are the powers or the exponents to which the fundamental or the base quantities are raised in order to get a required quantity. Alright, that's what the definition of dimension is. Okay, I told you before. And after that is momentum. For this case, or momentum also we may write that dimensions of momentum are 1, 1 and minus 1 on M, L and T. Is it clear? I hope it is clear. So it is actually the powers of the exponents, right? So in talking about the dimension, we must say about the powers or the exponents to which the fundamental or the base quantities are raised in order to get a desired quantity. But the thing that we are writing within the box bracket and including the box brackets is the dimensional formula. All right, dimensional formula is the one which we are writing inside the box bracket, including the brackets themselves. All right, dimensional formula, this one is dimensional formula. Dimensional formula, and this one as well, dimensional formula. Keep it in mind. If you are asked the dimensional formula, then you must tell everything including the box brackets. You must write actually. Okay, in case it is asked in the examination. And if you are asked about the dimension, then you have to mention just the powers to which the base quantities are raised along with the base quantities in respective order. Am I clear? Alright, so after that I'm giving you some more examples. The next one I want to tell you is acceleration. What is acceleration? What is the formula for acceleration? Tell me. Formula for acceleration is change in velocity by change in time, isn't it? Change in velocity by the change in time. What velocity is? Can you tell me? Can you tell me what velocity is? Velocity is actually nothing but displacement per unit time, right? That's what I told you before already. Displacement per unit time. Displacement per unit time. And in denominator there is another time. So all that you're getting in the end is, what is displacement? It's nothing but a length. And what is time? It is t, capital T, with which we denote time, and in denominator also time. So all we are getting is Lt to the power minus 2, isn't it? So in the dimensional formula you may write with capital M as well, m to the power 0, L to the power 1 and T to the power minus 2. Alright, so the dimensions are necessarily 0, 1 and minus 2 on M, L and T. Dimensions are 0, 1 and minus 2 on M, L and T. Alright, is it clear? Am I clear? I hope it's clear to you. So this is very important, keep it in mind. This is very important to remember the dimension of acceleration, because you have to remember the dimension of force. Yes, that is very important, because in many other quantities you will require the dimension of force, so commit it to memory. Okay, all right. So what should be the dimension of force? Let us find it out as well. Force equal to mass multiplied by acceleration, right? Mass multiplied by acceleration. Mass is capital M and acceleration we got already, LT to the power minus 2, right? LT to the power minus 2. Okay, so what we are getting finally is M LT to the power minus 2. Okay, or you may also write M to the power 1, L to the power 1 and T to the power minus 2. Writing 1 as the exponent is not essential and indispensable, right? You may or may not write it. Simply if you write M L T to the power minus 2, that creates no problem, and that is just exactly the same as M to the power 1, L to the power 1 and T to the power minus 2. All can easily understand, right? So you may also write like this: dimensional formula of force is equal to mlt to the power minus 2. Keep this in mind. This is very important, because in deriving or in getting or in finding out the dimensional formula of many other quantities, you have to make use of this relation, this formula for the dimensional formula for force, right? This is very important, so keep it in mind. After that, so let me tell you some other quantities of work or energy. Work or energy are basically two similar things, very similar things. Okay, you all have already gone through the work energy theorem. You all have understood in your very 10th standard, right? Work can be converted into energy and vice versa, and these two things are measured in the same SI units, right? So work and energy are synonymous, almost similar quantities. The dimensional formula or the dimensions of work or energy are necessarily the same, right? So let us find it out as well. What is work? How is work done measured? So work is basically force multiplied by the displacement, right? F into S. Okay, you might have done the formula for finding the work done in your ICC class 10 standard. Force multiplied by displacement. So dimensions of force will have to be used here, which is mlt to the power minus 2 multiplied by displacement, which is nothing but L, right? So afterwards you are finally getting m L square t to the power minus 2. Alright, this is what the dimensional formula for work or energy is, and the dimensions are 1, 2 and minus 2 on m, L and t, right? Am I clear? After that, okay, I'm showing you the dimensional formula for kinetic energy or potential energy. You tell me yourself, what should be the dimensional formula for kinetic energy? Kinetic energy or potential energy. Kinetic energy or potential energy. I did it just before, work or energy. So kinetic or potential, this is just two different forms of energy, right? So whatever kind of energy be it, the dimensional formula is just the same, that is m L square and t to the power minus 2. Is it clear? After that, this topic is actually endless topic, right? All that you have to get and understand is the concept, right? The concept behind this topic, and so many kinds of physical quantities are going to come. Almost uncountable number of physical quantities you are going to come across during your course of class 11 and 12. Okay, let me tell you that within the entire course of your class 11 and 12, you are going to come across almost 200 or 250 to 250 different physical quantities, which are still unknown to you. After your class 10 standard, you have not been familiar with those physical quantities. Yes, these things are going to come one by one in different chapters of your study. Alright, so one by one the chapters will come. You will start getting familiar with newer and newer physical quantities. Okay, so then you have to understand what the physical quantity is and how is it measured, what is its formula. After you get to know the formula of the physical quantities, you have to find the dimensional formula of that very physical quantities right in that chapter. Is it clear? This topic is literally endless still. Okay, I'm showing you a few unknown physical quantities which are still unknown to you but are going to come in the long run and in near future as well. Okay, a few such physical quantities are okay. I'm going to show you. Okay, have patience and be attentive. Next one I'm going to show you is moment of inertia. Next one I'm going to show you is moment of inertia. Okay, you might not have heard and you have not heard yet if you're just in class 11 beginning, you're watching this video. What is the formula for moment of inertia? It is denoted by capital I. Moment of inertia is actually m into d square. D is distance, just a distance. D is actually the radius from the axis of rotation. You will get to know as you will come across this topic. Okay. So the dimensional formula for capital I or moment of inertia is going to be m into what is d or distance is L, right? That is nothing but a length. M L square is supposed to be the dimensional formula for moment of inertia. Is it right? So this you can simply write m to the power 1, L to the power 2, T to the power 0. Because I told you, if you want, you may write all these three fundamental quantities: mass, length and time. Okay, if time is not included in the dimensional formula, just write capital T whole to the power 0, right? Because capital T whole to the power 0 is nothing but it's 1. Okay, that will not make a difference. Okay, that's how we respect all these three main fundamental quantities, right? Length, mass and time are the three main fundamental quantities. Okay, so which are always okay, prefer to be written in the dimensional formula of a physical quantity. Am I clear? Right. After that, I'll show you surface tension. What is surface tension? A chapter you will have in class 11, and there you'll have to know this topic, surface tension. The chapter is named itself is surface tension. This is symbolized with capital T, force per unit. Length, force per unit length is surface tension. So what is the dimensional formula for force? I told you to commit to memory. I told you to learn by heart a few minutes ago. What is it? See, this still is written on the board here. mlt to the power minus 2. Yes, this is very, very important. Commit it to memory instantly. So don't try to forget it ever. Otherwise, you're going to fall into the ditch, right? mlt to the power minus 2 divided by L. Capital L, okay, have cancelled each other. So all that you are left with is m to the power 1, L to the power 0, T to the power minus 2, right? So the dimensions of surface tension are 1, 0 and minus 2 on capital M, capital L and capital T. Is it clear? I hope it is clear. After that is torque. So let me scroll the board up. After that is torque. Torque is moment of a force, right? Torque or moment of a force denoted with tau, Greek letter. Force multiplied by a distance of the point of application of the force from the axis of rotation. Perpendicular distance it is actually. Indeed, it is the perpendicular distance. What is force? Tell me. What is force? mlt to the power minus 2. Isn't it? mlt to the power minus 2 multiplied by d. What is d? D is perpendicular distance of the point of application of the force from the axis of rotation. That is nothing but L, right? So the formula for torque is going to be m L square T to the power minus 2. Clear? Is it clear? M to the power 1 you may also write, no problem. L to the power 2, T to the power minus 2. After that is stress. All you are feeling why stress is coming here, because this topic is not at all a stress. This topic is such an easy topic. Okay, it should have been easy by now. Okay, as I'm trying my best to make you understand. Stress is not the mental stress or tension which you may be thinking already. This stress is actually force per unit cross sectional area, the restoring force actually it is per unit cross sectional area. Yes, that is something which you're going to come across in chapter of elasticity in your class 11 syllabus, right? Stress is actually force per unit area, F by A. So from here we can find out the dimensional formula for stress as well. So in place of F, we may write mLT to the power minus 2. Now, by now you have already got to understand how important the dimensional formula for force is, right? Because that is being used so frequently, so often that is being used. So in place of F, so I'm writing mLT to the power minus 2. What is area? What is cross sectional area? Area is actually length multiplied by breadth, right? So it is actually length into length or length square, we may write, right? So after that, what we are left with finally is m to the power 1, L to the power minus 1 and T to the power minus 2. Yes, that is what the dimensional formula for stress is. And in telling the dimensions, what we have to say is dimensions of stress are 1, minus 1 and minus 2 on M, L and T. Am I clear? I hope it is clear to all of you. After that, okay, I must tell you strain. This is also another physical quantity which will get in that very chapter of elasticity, okay, in which you are getting stress. All right, strain is actually change in length per unit original length, change in length per unit original length, or the formula for that you may write change in length per unit original length. So in numerator is L, in denominator is L also. So L and L are cancelling each other. So this is simply a dimensionless quantity. Well, you can write m to the power 0, L to the power 0 or and T to the power 0 within the box bracket. This is a dimensionless quantity. Keep it in mind. In your course of physics, you will come across many such quantities which have no dimension at all, because the formula for finding the value of those quantities are such that all the quantities in numerator and denominator are mutually cancelling each other. So no single physical quantity is left. All right. So those physical quantities are said to be dimensionless physical quantities. The quantities which are simply the ratio of two similar physical quantities are dimensionless. A few more such examples I'm going to give you. Okay, right. Some other dimensionless physical quantities. Some other dimensionless physical quantities. Some other dimensionless physical quantities. First one I want to tell you is specific gravity. Specific gravity. What is specific gravity? Specific gravity is a ratio of the mass of the body to the mass of an equal volume of water, right? Mass of the body by the mass of an equal volume of water. Equal volume of water. So you can clearly understand, you can clearly see that in numerator and denominator in both the places are masses, two masses, right? So what should be the dimensional formula? Mass and mass are cancelling each other from top and bottom, right? So all we are left with is nothing, m to the power 0, L to the power 0 and T to the power 0. If we are to write the dimensional formula somehow, then we have to write in this way, or else we may simply declare that specific gravity is a dimensionless quantity. It has no dimension, it has no unit as well. Okay, dimensionless as well as unitless quantity. The previous one, which was strain, delta L by L, was also a dimensionless and unitless quantity. This one, specific gravity as well, is a dimensionless and a unitless quantity. Keep these things in mind. After that, I want to tell you refractive index. Okay, you must have heard about the refractive index in your class 10 syllabus of physics. Can you tell me what refractive index is? Refractive index, mu, is a symbol with which we denote refractive index. What is refractive index? Refractive index is actually the ratio of two velocities, the velocity of light in medium 1 to the velocity of light in medium 2. Yes, if a ray of light is traveling from one medium to another medium, okay, then the ratio of the velocities of light in the first medium to that in the second medium is called the refractive index of the second medium with respect to the first medium. Keep it in mind. So this is actually 1 mu 2. 1 mu 2 is the refractive index of medium 2 with respect to medium 1, right? B1 by B2. Okay, according to Snell's law, this is written as sin I by sin R. Okay, you must be thinking about that we got to learn Snell's law, and that was saying sin I by sin R. In that case also, you see sin I and sin R both are ratios. Sin is actually perpendicular by hypotenuse of a right angle triangle, right? So sin itself is a ratio, sin I is a ratio, sin R is a ratio, sin I and sin R both themselves are unitless. So the ratio of two ratios is also a ratio, simple ratio, which have no dimension, which is no units as well, right? So from that aspect also, refractive index is becoming a dimensionless and okay and unitless. What should be the dimension of velocity? Tell me. Dimension of velocity, okay, I showed you in the very beginning, lt to the power minus 1, right? In denominator also, all we have to write is lt to the power minus 1. So both are mutually cancelling out each other, and all we are left with is nothing, m to the power 0, l to the power 0, and t to the power 0, and we can write this is dimensionless. This is dimensionless. Dimensionless. This is dimensionless also. Specific gravity, I showed you before. Okay. This topic is literally endless, believe me. In class 11th 12th standard, within your entire course of physics, you will come across at least 250 to 300 such physical quantities, different physical quantities, some of which may be known to you, the majority of which will be unknown to you. You have to know the physical quantities, know the definitions, understand them, and know their formula, okay, the formula with which we find them out. And after that, you have to get the dimensional formula for those physical quantities one by one. And finding the dimensional formula of all those unknown physical quantities is also a part and parcel of the chapter. Keep it in mind. So don't try to skip it. For every chapter, whatever new physical quantities, okay, you will come across, make sure to find out the dimensional formula and SI unit of that physical quantity. Alright. So let's come to some others. Next one I will show you is potential difference. What is potential difference? Potential difference is a physical quantity which we will have in electrostatics and current electricity. Formula for potential difference is equal to work done per unit charge, W by Q. Work done per unit charge. What is work done? We did it before already, right, in this class. Work done is equal to force multiplied by displacement, right? Force multiplied by displacement. And what is charge? You know, charge is not a fundamental physical quantity. Yes, it has not been given the honor of a fundamental physical quantity. Fundamental physical quantity is current, electric current. Okay, so charge is nothing but electric current multiplied by time, isn't it? Electric current multiplied by time. So let me write the names first. After that, I'll come to the symbols. Current into the time. Current into the time. Okay. Then in place of force, we may write the dimensional formula for force, mlt to the power minus 2. See how important the dimensions for force is. Multiplied by displacement L, and in denominator is coming current, that is I. I showed you the symbol for current I, and here we are taking as I. In some other books it's taken as capital A, which is actually the unit of current, ampere. Okay, and here we are taking it as capital I into time. Time is T, capital T, right? So the thing that we are getting ultimately is m to the power 1, L to the power 2, T to the power minus 3, and A to the power minus 1. Isn't it? Isn't it? Yes. So the dimensions of PD यानी कि potential difference are 1, 2, minus 3 and minus 1 on M, L, T and A. Alright. After that, so let me tell you the dimensional formula of a few constants such as Boltzmann constant. Okay, that you know what is NEET examination? NEET is an all India level competitive examination for entering into medical science, right? In NEET examination, it had come Boltzmann constant. Boltzmann constant. The symbol with which you denote it is K, small k. The equation we shall make use of here is PV equal to KT. What is K? K itself is a Boltzmann constant. This equation is true for one molecule of an ideal gas. For one molecule of an ideal gas. You know, for 1 mole of an ideal gas, we have the ideal gas equation PV equal to RT, and you know that R is the universal gas constant here, and for 1 molecule the equation gets modified to PV equal to KT, because you know in 1 molecule, in 1 mole of any ideal gas, there are Avogadro's number of molecules, capital N number of molecules. So in for 1 molecule the equation gets modified to PV equal to KT, because K is equal to R by capital N, 6.022 into 10 to the power 23. Okay, that is Avogadro's number. Alright, so the equation PV equal to KT is going to be applied here in finding out the Boltzmann constant, in finding out the dimensional formula for Boltzmann constant. What is K? K is equal to PV divided by T, right? So here what is P? P is pressure. In place of pressure we can write F by A, thrust per unit area. Thrust is nothing but a force, you know, perpendicularly acting force is what we call a thrust. Okay, so force by area, and what is volume? Volume equal to area multiplied by the length, and in denominator is temperature. This is not time. Don't make the blunder of writing this as capital T. T will be changed to theta, because T here is temperature. PV equal to KT. K is Boltzmann constant, P is pressure, V is volume, and T is temperature, right? So in place of T we should write theta. Okay, so A and A are cancelling out here. So in place of A we shall write M L T to the power minus 2 multiplied by L divided by theta. And then finally the dimensional formula for Boltzmann constant is coming out as M to the power 1, L to the power 2, T to the power minus 2, theta to the power minus 1. Yes. So the dimensions for Boltzmann constant K are 1, 2, minus 2 and minus 1. 1, 2, minus 2 and minus 1 on M, L, T and theta, right? That's how we shall write. So another constant, okay, I want to tell you is Planck constant. Another constant I want to tell you, and that had come in the joint entrance examination, which is Planck constant. Planck's constant. Max Planck was a scientist, a very popular scientist, which is known for discovering the particle nature of light. Max Planck. You may or may not have heard his name. Max Planck was a very renowned scientist who is famous for finding the particle nature of light. Particle nature of light. particle nature of light. Okay, he discovered, and that is a major contribution of this great scientist Max Planck. In honor of his name, we have introduced a constant which is known as Planck's constant, that is small h, as its symbol is. Actually, the equation we shall make use of here is E equal to hf. E equal to hf. Energy of a photon. What is E? Is actually energy of a photon. Energy of a photon. What is a photon? A particle of light. Small particle of light. Tiny particle of light. Energy of a photon. H is Planck's constant. What is F? F is frequency. Have you known the formula for the frequency? Yes, frequency is reciprocal of time period, right? So 1 by t. Frequency is nothing but 1 by t. So in order to find the dimensions for h, we can write h in terms of E and F. E by F. What is E? E is nothing but energy. And what is energy? Energy is nothing but work done. And in denominator is frequency. Frequency, in place of frequency we can write 1 by time. 1 by time. All right, in place of W or work done, we can write F into L is displacement, force into the displacement. All right, force into displacement, and 1 by t is getting as t in numerator. All right, so in place of F you write the dimension for force m L t to the power minus 2 into L into t. So finally the dimensional formula for Planck's constant is coming out as m L square t to the power minus 1, isn't it? M L square t to the power minus 1, or m to the power of 1 you may also write. Okay, so here the point to be noted is that h, which is Planck's constant, is just a proportionality constant. Actually the thing is E is proportional to F. Energy of a photon is proportional to the frequency. So after that is coming the Planck's constant, E equal to h. So h is nothing but a proportionality constant. So keep in mind that proportionality constants may not be dimensionless always. Proportionality constants, keep it in mind. Proportionality constants may have dimensions. Proportionality constants may have dimensions. All right. Now I will tell you another constant, which is gravitational constant. Gravitational constant. Gravitational constant capital G. All right. Gravitational constant capital G. Okay, if you have to find the dimensional formula for gravitational constant, you need to know Newton's universal law of gravitation. What does it say? F is equal to G into m1 m2 by r square. All right, from here you have to get the formula for G. G equal to F into r square divided by m1 into m2. All right, then write the dimensions of what is F. F is force. What is R? R is distance of separation between the masses, point masses. M1 and M2 just two masses. All right, so in place of F you write m L t to the power minus 2. In place of r square you just write L square, because R is distance of separation. In place of m1 m2 you may write m square. All right, so finally the dimensional formula for G, we are getting m to the power minus 1, L to the power plus 3, and t to the power minus 2, isn't it? Yes, m to the power minus 1, L to the power plus 3, and t to the power minus 2. So the dimensions are minus 1, plus 3, and minus 2 on m, L, and t respectively. All right. The next physical quantity I will tell you is angular velocity. This angular velocity, that is omega equal to v by r. V is linear velocity, right? What is linear velocity? That is nothing but displacement per unit time. And in denominator is radius, which is nothing but a length only, capital L. So what is displacement? L by time t divided by L. L and L are cancelling each other, so that is 1 by t, or t to the power minus 1 is the dimension, and that is actually the same as the dimension of frequency. Same as the dimension of frequency. Same as the dimension of frequency. Isn't it? So what is frequency? A few minutes ago I told you only that frequency is reciprocal of time period. So 1 by t means t to the power minus 1, isn't it? So keep it in mind that angular velocity omega and frequency f have the same dimensions. Alright. After that is momentum, angular momentum. I will tell you. Angular momentum. Angular momentum. Angular momentum equal to mvr, mass into velocity, that is linear velocity, into the radius. Mass means m should come, capital M. V means L t to the power minus 1 should come. R is nothing but a length, another L should come, right? So all you are getting finally is m L square t to the power minus 1. Okay, m L square t to the power minus 1. So the dimensions of 1, 2 and minus 1 on m, L and t only. Next will come to resistance. Next will come to resistance. Another thing which you had done in current electricity. Okay, resistance R is equal to V by I, potential difference by electric current. What is potential difference? Potential difference B is equal to W divided by Q. W divided by Q, work done per unit charge. And what is current? Current is actually charge per unit time, charge per unit time, capital T. And so what is W by Q, T by Q, right? Q, right? And what is W? Force into the displacement. Force into the displacement. Force into the displacement multiplied by time T divided by Q. Q is actually current into the time, current into time, and Q is squared here in denominator, current into time whole square, right? In place of force we write m L t to the power minus 2. In place of displacement we write another L. In place of T we write T. In place of current we write E. In place of time we write T, and we make them squared. All right. And so all you are getting finally is C M, and here is one L and L square, and then here is t to the power minus 2 and t to the power minus 1, and below is t square, so t to the power minus 3 it's coming finally, and then a to the power minus 2, because in denominator there is a square, a to the power minus 2. All right, that is what the dimensions for resistance is coming. M to the power 1, L to the power 2, T to the power minus 3, and A to the power minus 2. So in talking about the dimensions, we have to tell 1, 2, minus 3 and minus 2 on M, L, T and A respectively. Is it clear? And after that is density. What is density? Density rho equal to mass by volume. You all know this. This is very simple from very lower classes. Okay, you have been getting this topic. Density rho equal to mass per unit volume. Mass means m only, volume is actually L cube, right? Length into breadth into height, basically where the volume is. So it's m L to the power minus 3 and T to the power 0. That is what the dimensional formula of densities. After that is angle. Angle or theta. Angle and angles which is theta is actually arc by the radius, S by R. Angle equal to arc by radius. Okay, for a circle, angle theta which is subtended at its center is actually arc by radius. This is actually S, arc. Alright, and this is the radius. Arc by radius is the angle, and both are actually nothing but lengths. So arc by radius is actually L by L, which are cancelling each other, and this is a dimensionless quantity. M to the power 0, L to the power 0, and T to the power 0. Dimensionless quantity, but not unitless. Keep it in mind. Yes, all dimensionless quantities are not unitless. There are some exceptions, right? One such exception is angle, dimensionless but having units. Dimensionless but have unit, but has unit. What is its unit? Unit is radian. Okay, the unit is radian. Unit is radian. Okay, so one more such thing is solid angle. One more such thing is solid angle. That will come, afterwards in your course of syllabus. Solid angle is also a unitless quantity. I'm so sorry, this is a dimensionless quantity but not unitless, just like angle. It's dimensionless but having a unit. The unit is radian. Alright. So these are two important things. Keep in mind: physical quantities. Physical quantities having units but no dimensions. Physical quantities having units but no dimensions. Examples are angle and solid angle. Angle and solid angle. Okay, so these two are really exceptions. Such physical quantities may be asked in your examination or in some competitive examinations as well. So in that case you have to write these two examples, angle and solid angle. These are physical quantities which have no dimensions but have units, right? The units are radian and sterradian. But physical quantities which have dimensions but no units are nothing. No such physical quantities exist out there. Physical quantities having dimensions but no units. No units are nothing. Nothing can exist out there which have a dimension but no units. Yes, quantities exist out there which have units but no dimensions. Okay, the examples of which I've given have already, angles and solid angle. But no such physical quantities exist out there which have dimensions but no units. Keep it in mind. Isn't it interesting? These two are really exceptions, angles and solid angles. Keep it in mind. Up to this, in this video, I just tried my best to explain you what dimensions is and how to find the dimensional formula of the physical quantities. So many such physical quantities you are going to come across afterwards in different chapters, newer physical quantities which you have to understand. The formula for finding out the values of those physical quantities you have to know, and after that you yourselves have to find out the dimensional formulas of those physical quantities. But this topic is not ending over here. This topic has a later portion which is principle of homogeneity, and by making use of the principle of homogeneity you have to find out the dimensional formulas of different unknown quantities and terms and symbols which will be involved in different equations which will be given to you. That is very important, especially keeping in mind the competitive examinations like joint entrance examination and NEET examination. So make sure to watch the second part of this video. Alright, till then, bye bye, take care.